Okay. Hello, everyone. And let me start by thanking the organizers for putting together this wonderful workshop. I'm going to talk about how to map these Moiré homobilayer TMDs to a Landau level problem. This is work done in collaboration with Naming Wei, Jingtian Shi, and our supervisor, Alan McDonald. And this is the reference if you're interested in. So the motivation, it's very clear, is this recent observation of fractional quantum anomalous Hall states or fractional Chern insulating states in MOT2, first by optical measurements, but also later confirmed by transport experiments, which show a very neat, very well quantized transport at several fractional fillings of this Moiré band. But then, so these experiments are very nice, but there's many open questions. For instance, they see a state at 2/3, but they don't see the counterpart at 1/3, or they see this very interesting state at 1/2, as Professor Shu was mentioning, and we would like to address the nature of these states. So the way we'll do it is theoretically starting from the continuum model for Moiré TMDs. So yeah, this is a model that for those of you that are more familiar with the Stritzer-McDonald model is like the BM model for TMDs. It's supposed to describe all TMDs, but in this talk, I'll focus on homobilayers, and I will focus on the K-Valley projected Hamiltonian. There is an additional time reversal partner for the K-prime valley. And the model consists of, in the diagonals, it's a parabolic dispersion for carriers living in the either top or bottom layer, plus a Moiré potential, because one layer feels the presence of the other through the Moiré potential, and then you have some interlayer tunneling terms. And here I show how the Moiré potential and the interlayer potential are written. And you see that this model depends on 3 parameters. This BM that tells you the strength of the Moiré potential, so how deep the Moiré potential is. This psi parameter is the shape of the Moiré potential, so it can be triangular or honeycomb. And finally, omega is just the strength of the interlayer tunneling. And interestingly, what was shown in this early reference by Feng-Shen Wu and Ellen is that depending on the parameters you choose to diagonalize your Hamiltonian, you will get a topmost relatively flat band that can be trivial or topological. Now, the values, the exact values of these parameters vary from material to material. But you can go ahead and, for example, obtain a phase diagram for this continuum model as a function of some of these parameters. So what I'm showing here is the bandwidth of this topmost flat band as a function of twist angle and of the continuum model parameter psi. And you identify a regime where the topmost band is trivial and another regime where the topmost band has Chern number either plus or minus 1. Now, an interesting observation done by Liang Fu's group is that in the non-topological regime, the behavior of the bandwidth twist angle is monotonic. But however, if you go to the topological regime, you get a magic angle. You get an angle where the band becomes almost flat. And because we have a very flat Chern band, this motivates, this raises the possibility of stabilizing fractional Chern insulating states. And this motivated several groups, including us, to do exact diagonalization calculations to give evidence for these states. And we also realized that very close to the magic angle, the quantum geometry of the band is nearly ideal. And what this means is that there should be a connection of this band with the physics of the lowest Landau level. Now, numerical studies like this allow you to track the phase diagram and maybe study the competition of the fractional quantum Hall phase with charge density waves, for instance, or other competing phases, but they don't really tell you why do you have a magic angle or why the quantum geometry is so close to ideal. So in order to try to address this question, let me go back to the continuum model and write it in layer space in terms of Pauli matrices, when I introduce this delta node and these delta functions. And you can see that the continuum model can be rewritten in a way that it looks like a fermion in the presence of a pseudo-spin field. And then if you plot how this pseudo-spin field looks, you see that it has a texture and that it has 1 skyrmion per Moiré unit cell. So you can see this as like the spin of the electron aligns with the pseudo-spin field of the skyrmion, and it acquires a very phase as it goes through the unit cell. Now, the winding number of this skyrmion does not coincide always with the Chern number of the topmost band. There's additional requirements that are needed, and that's what I'm going to try to tell you in the next few minutes. So in order to do it, let me take this Hamiltonian and apply a unitary transformation. So at every point in space, I will rotate the direction of the skyrmion to point in the plus C direction. And when you do that, the Hamiltonian gains an effective periodic magnetic field. But this is a matrix problem, right? This has layered degree of freedom. So the way to see it is like you have in the up and down pseudospin sectors, you have like a particle in a magnetic field separated by a Zeeman splitting, which is given by the magnitude of this skyrmion field. And in the limit where this magnitude of the skyrmion field is much larger than the kinetic energy, you can just project the low energy physics to the up sector for holes. And you end up with a scalar Hamiltonian, which is given here, and the effective magnetic field is obtained from the effective vector potential. Now, the trick is that this magnetic field is a periodic function with the Morales periodicity, but it has a non-zero mean. So I will separate the magnetic field into its constant part and the periodic part. And this allows me to split the Hamiltonian into the Landau levels, the Landau levels for the constant part, and then all the rest I will rewrite as a periodic effective potential. So the Landau levels, the part of the Landau levels, they have a splitting that grows quadratically with twist angle. So for very small twist angles, you will have very close together Landau levels, while if you increase the twist angle, they will separate. The green line here is the effective Zeeman separation between the two pseudospin sectors. So when this energy scale is the largest, this means that this adiabatic approximation, this projection to just one of the two sectors is faithful. And finally, in red, I'm showing the matrix elements that would mix the zeroth and the first Landau level. So interestingly, you see that there is a region where the Landau level splitting is much larger than the Landau level mixing. So it's further motivated to project just to the lowest Landau level. So I will do it. And to do it, it's convenient to notice that these functions that enter in the Hamiltonian, A, D, and delta are periodic. So I can write them down as their Fourier expansions. And if I write down the Hamiltonian projected to the lowest Landau level in the Landau gauge, this is how it looks. And then the red part is an effective periodic potential where the Fourier coefficients are given by this expression here. And the M subscript just tells you how many shells in reciprocal lattice vectors am I taking. Now, because this plane wave matrix element has this magnetic form factor that goes like e to the minus g squared, it's still a good approach. It's justified to just truncate the potential to the first shell of reciprocal lattice vectors because higher contributions will get knocked down. So I'll do it, and when we do it, this is a nice limit because the problem has an analytic solution. And the picture is that you have a bunch of Landau levels, but because you have a potential, they will acquire some dispersion. And in the end, you have bands whose bandwidth is given by this expression that depends on a single parameter, or the C1 parameter. I am explicitly writing how this parameter behaves, but the bottom line is that there is a term that you can show that is always positive. And then there is this term, which is the first Fourier coefficient of the magnitude of the skyrmion field. And what you can think about is if this delta 1 is negative, there will be a twist angle for which this C1 will vanish. And then you get a flat band, which implies a magic angle. So how does this delta 1 looks? And this is how it looks. So you see that as a function of continuum model parameters, there is a region where it's negative. And you see that if you plot the topological phase diagram of the continuum model, the region where this delta 1 becomes negative, it coincides with the region where you have topological bands. And this means that it's not enough to have this layer pseudospin degree of freedom. It's also important, the shape of the skyrmion texture is important for the emergence of topological bands. So this is how this C1 looks. And you see that where it vanishes, that's the position of the magic angle. So in purple, I'm showing the bandwidth of my effective model. And in blue, I'm showing the bandwidth of the continuum model as a function of twist angle. We get a fairly good agreement in magic angles. Let me just mention that for these calculations, we use the parameters obtained in this initial paper by Feng, Sheng, and Alan. But if you use more updated DFT results, you obtain something like around 3.7, which is close to the experimental value and the experiments by Professor Xu. Just to make a connection with the previous talk, there is another way to see this, and it's invoking this result by Aharonov and Kasher for a spin 1/2 particle in a magnetic field that has a manifold of zero ground state due to a cancellation between the 0-point energy of the Landau level and the Zeeman field. So if I had rewritten my Hamiltonian, not separating the constant and the periodic part, I can rewrite it as Hamiltonian that has the Aharonov-Kasher form plus some leftover terms. And it can be shown that when this at the magic angle, these leftover terms exactly cancel out, and there you have, you have a Hamiltonian that is bound to have a flat band. So this brings me to the end of my talk. So let me just mention that I presented a way to map this continuum model of Moiré TMDs to a Landau level problem, which is more familiar to many of us. The way we did it is using the layer pseudo-spin degree of freedom and doing an adiabatic approximation for small twist angles, and then realizing that for large twist angles, we can project to the lowest Landau level. We obtain a parameter, a model that depends on a single parameter. It explains the emergence of a magic angle. It explains why the quantum geometry is nearly ideal, because a Landau level has ideal quantum geometry. And finally, it tells you that fractional chain insulators are bound to appear in these systems. And we are working in some future directions, trying to include Landau level mixing and include interactions in this from this perspective. And I'm happy to chat about it if you guys have questions. So thank you for your attention.
Very nice talk. So I'm wondering, is that possible to use this construction to help guide us to find the term bands correspond to the seconds?
Yeah, that's something we would like to do. I guess you are thinking on non-abelian states. So if this, if this mapping is faithful, you can think that the second Landau level here would correspond to the second band in the Moiré system. So I think this construction would be useful. You would need to find a region where the second band is flat and well isolated from the others. So yeah, maybe it's a good way to do it. We're thinking about it too. So this is a calculation from the Xiao's group in Washington. I think it's just uniaxial strain, but I'm not sure. I don't know. I guess it's just a correction that modifies the continuum model parameters, but it should be taken into account.